organic matter react with fluorine or with other chemical oxidant like monochlorine to produce disinfection byproducts. Disinfection byproducts have to be avoided because they are mainly toxic, very toxic. So oxidation provides to the removal of organic contaminants or inorganic compounds. And the last one, for the disinfection, the chemical oxidant provides the disinfection at the output of the treatment plant, and also during the transfer in the distribution system to avoid the formation or the increase, the buildup of the biofilm. So what is a biofilm? I don't want to speak a lot about biofilm because you see it previously with Christine. It's a complex structure which adheres to every solid surface in a wet environment or in aqueous environment. And in water, more than 90% of the microorganisms are found in biofilm instead of planktonic cells. There is 3 key components in the biofilm. Of course, the biological one with the bacteria, protozoa, viruses, algae, fungi. And there is another component which is the organic one with the EPS, so the extra-polymeric substances excreted directly by the microorganism, mainly composed by proteins and polysaccharides, and which constitute the gel matrix of the biofilm. And this matrix gives mechanical and chemical structure to the biofilm and protect microorganisms from the oxidant, for example. There is also mineral inorganic components. Depending on the composition of the water, we can find calcium, iron, aluminum, for example. And if we consider a distribution system, this is the different step of the formation and detachment of a biofilm in a pipe, for example. So first, you have a primary adhesion. That is to say, you have the transport and absorption of inorganic and organic elements to the surface of the pipe, the adhesion of microorganisms. Usually, this primary adhesion is reversible with a wash, with a simple water wash, for example. Then you have the secondary adhesion, which is more irreversible. That is to say, here the microorganisms are protected by the EPS matrix and they cannot be removed by a simple water wash, for example. Then the maturation phase, you have the increase of the biofilm. It is the population quickly increased. The microorganism population quickly increased in the biofilm. And then, finally, when the biofilm reaches a certain size, you have detachment of part of the biofilm directly in the water flow. So, detachment is very important regarding to the quality of the water. And you have two kinds of process. First, the most frequent erosion. It is detachment of small quantity of biofilm, small aggregates, and generally there is no problem regarding to the water quality of guidelines. And another one is sloughing. This is the detachment of larger fraction of the biomass, and sometimes, generally, it presents a risk for the water quality study. So, in this table, there is some waterborne diseases due to microorganisms present in the water. But I don't want to detail these two tables because there is another one, but just to show you that there is diseases due to bacteria, waterborne bacteria, and also protozoa, and also viruses. So we need disinfection to remove all these pathogens from water. And how to measure the efficiency of disinfection? We have a parameter called CT, C for concentration of residual concentration of oxidant, and T, time contact between water and the oxidant. It is a kinetic law based on some hypotheses. First, the microorganisms are uniformly dispersed and have an equal susceptibility to the oxidant. The disinfectant concentration is L constant during the experiment, and we have a kinetic law. First order regarding to microorganism and N order regarding to oxidant concentration. So we have this kinetic law, Chrition law, which make a link between the removal of the microorganism, the rate of the removal of microorganism, and C, the residual concentration of oxidant, and it's a rate constant. We can simplify this expression, mathematical expression, because the little n equal 1 in most of the cases. So we have directly this relation between the residual of the microorganism and the number of microorganisms at the end of the experiment, for example, and N0 at the beginning of the experiment, directly related to K, the rate constant, and CT, the parameters. So this is important, not T alone or not C alone, but the product CT is important to measure the efficiency of the disinfection. In this tab we have some order of magnitude of the value of CT for 99% of inactivation of removal, that is to say 2 logs of removal of microorganism removal, and this for 2 oxidants, chlorine and ozone, and for example, bacteria, virus, and protozoans. And you can see if the value of CT is low, that is to say, for example, for Escherichia coli, the microorganism is very sensitive to this oxidant. While when the CT value is high, that is to say, the microorganism is very resistant to this oxidant. So you can see that bacteria are more sensible than virus and then protozoan generally. And if we compare the 2 oxidants, you can see ozone is a better oxidant to do disinfection than chlorine. But chlorine is a good disinfectant, nevertheless. So what should be an ideal oxidant? It must be strong to do a complete oxidation, or as far as possible complete oxidation of natural organic matter, micropollutants, and so on. It must be easy to handle, safely to handle too, highly soluble, non-toxic, and compatible with the material in contact with the water. For example, to avoid corrosion. Cheap, and very effective to do disinfection, a very large biocide properties. Persistent in the network for preventing the regrowth of the biofilm, and of course with no formation or low formation of toxic disinfection byproducts, DBPs, by reaction with the natural organic matter. And we know that diesel oxidant for water treatment doesn't exist, because, for example, ozone is a very, very good biocide, but is not persistent in the network. And chlorine is persistent, for example, but can produce, if we don't treat before the natural organic matter, chlorine can produce a large quantity of disinfection byproducts. So we can use chlorine almost in three forms, like gaseous chlorine, liquid chlorine as a bleach, hypochlorite, sodium hypochlorite, and solid form, calcium hypochlorite. Monochloramine, this is this form, and we can use also for water treatment, drinking water treatment, chlorine dioxide, for example, ozone, and other chemical oxidants not used in the field of drinking water treatment, but for other applications, for example, industrial oxidation. Other available treatments are possible. They are mainly physical treatment, like UV or membrane filtration. A few words on the chlorine chemistry and monochloramine chemistry in aqueous solution. Just to say, chlorine is a case, highly soluble in water, which quickly hydrolyzes to form hypochlorous acid, HECl. HECl is a weak base, it's a weak acid, sorry, and it dissociates to form the conjugated base, Cl-, hypochlorite ion. So there is an equilibrium constant which allow us to calculate the distribution of the different forms of chlorine in water in the range of in the pH range of water treatment. So you can see in this figure, in this graph, that chlorine as dissolved chlorine is not present above pH 4, for example. So in the field of water treatment, we have not this form, but we have only two forms, hypochlorite ion, here, for the higher pH values, and HOCl, hypochlorous acid, and here, this is the range, the pH range for water treatment, and you see you have the two forms. It is important because the two forms of chlorine in water have not the same reactivities with natural organic matters and with microorganisms. The most active is this form, HOCl, hypochlorous acid. So just to a few words. We call HOCl free active chlorine, and HOCl plus Cl- free available chlorine, free chlorine, and chloramine is called combined chlorine, and the total chlorine. So in the water you can have the two forms, free or combined, the total chlorine. And the most efficient is HOCl, the less efficient are the chloramines, regarding to oxidation purposes or disinfection purposes. So what is monochloramine? Monochloramine is a chemical oxidant produced by the reaction of chlorine on ammonia. It can be produced intentionally to do a treatment. For example, for drinking water in the US, Canada, Australia, or for the disinfection of cooling water treatment, for example, in France. But it can be also produced non-intentionally as a byproduct, I will say. For example, when you do chlorination of swimming pool, swimmer releases a lot of nitrogen compounds which can react with chlorine and form monochloramine or other chloramine. So the chloramines are formed by the reaction of chlorine as hypochlorous acid on ammonia. So we form first the monochloramine, then the dichloramine, and then the trichloramine, or nitrogen trichloride. All of these are combined chlorine. And the formation depends on the pH and the ratio chlorine to nitrogen ratio. Then we have a reaction of decomposition of chloramines involving both monochloramine and dichloramine to produce nitrogen. That is to say, we remove ammonia. And the global reaction to a special point called the breakpoint is this reaction. So we need 3 mole of chlorine per 2 mole of ammonia to eliminate, to remove ammonia from water. And that is to say, in a mass ratio, 7.6 grams of chlorine per gram of nitrogen to eliminate ammonia in water. So we have a typical curve called breakpoint curve, which describes these different reactions. And on the axis, and the x-axis, you have the chlorine dose added to the water containing ammonia, and in the y-axis, you have the residual chlorine measured after a contact time. This first part of the graph represents the formation of the chloramines, mono and also a few dichloramine. This part of the curve represents the destruction of the chloramines. That is to say, up to this point, you have only combined chlorine, mono, di, and a few mono, di, and a few trichloramine. And after this special breakpoint, that is to say 7.6 grams of chlorine per gram of nitrogen, you have free chlorine, as HCl. So it is very important, this curve. When you do monochlorination, you have to be in the first part of the curve, that is to say only the formation of monochloramine. And if you want to do chlorination, you have to be in the last part of this curve, where you have free chlorine available in the water. Another word about the reactivity of chlorine or monochloramine on bromide ion. Chlorine reacts quickly with bromide to form bromine as hypochlorous acid, and we have also the reaction of monochloramine with bromide to form bromochloramine. And it is very important because these two species are also oxidants, and even bromine as HOBr is much more oxidant than chlorine. So bromine can react with organic matter, natural organic matter, to form brominated compounds. So the system is quite complex because when you have chlorine and bromide, you form hypogromous acid and a strong oxidant. And with ammonia, you form chloramine. That bromine can react also with ammonia to form bromamine. And with chloramine to form bromochloramine. That is to say, all these species are alloamine or oxidants. And when you have organic matter, you will easily form disinfection byproducts or organohalide compounds like TOX, total organic halide, or AOX, adsorbable organic halide. So the families of DBPs, first I will say that there is more than 600 DBPs identified on chlorinated water, but almost this represents only 50% of the total organic alloy formed during chlorination. So we have a lot of work to identify the other sample, the other components. The familiars, mainly the trihalomethane, THMs, and the most known is chloroform. It was the first identified in chlorinated drinking water. And then we have also acid, alloacetic acid, this is the general formula, chlorinated, brominated, and mixed alloacetic acid, and other family like alloacetonitrile, alloketone, and allonitromethane, for example. But you have this table is too small, but you have a lot of products which have been identified in chlorinated water or disinfected water. For example, nitrosamine are typically produced with the use of monochlorine, not with the use of chlorine. So there is a lot of byproducts during the disinfection. Why it is important? It is important because these byproducts are toxic. And for example, for chloroform, it is known that this is a carcinogenic compounds to animals, and it has been classified as carcinogenic for human, group 2B, that is to say possibly carcinogenic to humans. And there is epidemiologic studies that show there is an association between exposure to THM, not only with drinking water, but also in a professional way, for example, with problem at the birth, low birth weight, premature birth, or problem during the pregnancy. And another word about the toxicity. We are interested now with nitrogen disinfection byproducts because studies have shown they are more cytotoxic and more genotoxic than the carboneous DBPs, the corresponding carboneous DBPs. For example, you can see in this slide, you can see in this slide, for example, alloacetonitrile, alloacetonide, allonitromethane are more cytotoxic or genotoxic than, for example, alloacetic acid, only carboneous DBPs. And also there is a problem with brominated, and if you have iodide in the water, you can form iodinated DBPs. And you have also strong differences between cytotoxicity and genotoxicity of the iodo and chloro compounds. They are more toxic than the chloro compounds. And nevertheless, the regulation in drinking water is only based on the chloro compounds and carboneous compounds. not only on chlorocarbon, only on carbonate compound, sorry. And for example, this table shows the regulation concerning the drinking water and the DBPs, and you have almost all the countries have a regulation concerning THM. For example, Switzerland has a drastic regulation of 25 microgram, it is in microgram per liter of compounds concerning THM. And we have also, for example, Australia with less drastic regulation with 250 microgram per liter of total THM. But also you can see there is countries who regulate other DBPs like alloacetic acid, for example. You can have a regulation of specific alloacetic acid due to their toxicity, for example. Just a word, bromate is found during ozonation, so it's a problem of ozonated water, and chlorate is found when you use chlorine dioxide. And NDAE, nitrosodimethylamine, is formed during only monochlorination. Now the practical aspects to do chlorination and to do monochlorination. I have to accelerate. So you have three forms to use chlorine when you do chlorination: chlorine gas, chlorine liquid chlorine as a sodium hypochlorite, and hypochlorite, calcium hypochlorite, solid hypochlorite. So for the gaseous chlorine, according to the necessary amount, the needed amount, you have a cylinder like this for the small capacity, or you have a large tank with high capacity when you have a huge drinking water plant. So due to the chlorine is hazardous, so you have to store chlorine in a specific room, generally outside the main plant, with a system of extractor fan, for example, ventilation, and with different alarm if you have a leakage of chlorine to stop the supply of chlorine. So you have generally several containers in parallel and a special device to switch from the empty container to the full container to ensure the continuous supply of the gaseous chlorine. And then chlorine is withdrawn from the tank or from the cylinder by this kind of device, a chlorinator. We have a venturi, and water passes through the venturi and there is a depression, so chlorine is sucked by this system, and you produce a chlorinated solution that will be injected directly in pipe for the treatment. For example, in this graph you can see the tank, the system of the chlorinator with the water, and you form the chlorinated water, inject it directly in the pipe, and a few meters after you have a sample with one to do the analysis of water and to control the injection of water, to have a residual chlorine, a fixed residual chlorine in the water. So you can use also chlorine as a bleach. So bleach is this solution, a very basic solution. We are pH more than 13, for example, and the concentration is high, about 150 grams of chlorine per liter, and is directly injected by a measuring pump, for example, in the pipe. And for solid chlorine, pellets like that. You have this kind of device with the storage of the calcium hypochlorite here.